bounded domains. And we'll first discuss the perfectly matched layer, which is a way to model unbounded wave propagation problems. In particular, we look at the acoustic wave propagation first in 1D, then we switch to a general formulation for the Helmholtz equation. So this is a 2D or 3D problem in the frequency domain. Then we'll apply this to transient problems and quickly also discuss practical application. And finally, I will show you how infinite mapping can be used to handle unbounded domains for elliptic partial differential equations. So let's look at open domain problems. If we have an infinite domain, we clearly cannot model it directly by the finite element method, because at some point we have to truncate our domain. Here we can set standard boundary conditions, Dirichlet-Neumann boundary conditions. However, they do not model infinity. So for wave propagation problems, we already have seen the absorbing boundary conditions, and another technique is called the perfectly matched layer. And so the idea here is that we surround our domain of interest, so our computational domain, here shown in the light gray, by a layer, which is supposed to model the infinite domain in an appropriate way. For wave propagation, this will be to absorb waves there, and for elliptic PDEs, we can apply mapping in this layer. Another technique there is to use so-called infinite elements at the boundary of our computational domain. So let's first look at the perfectly matched layer. Here we have our propagation region. So this is the domain of interest that we want to investigate, and we surround it by an additional layer. And the idea now is that waves propagate into this layer and they are not reflected back into the domain of interest. So in order not to be reflected back, obviously the waves must be damped in this layer. And the other requirement we have is that we must have perfect matching between the domain of interest and our absorption or perfectly matched layer, so that no reflections occur at this interface where we change from the propagation region into the damping layer region. So these perfectly matched layers have been an active topic of research since their introduction in the 70s, and the formulation you're seeing now will closely follow the book by Manfred Kaltenbacher in the reference 2. And in there you can also find a lot of additional references if you're interested in perfectly matched layers. So we'll focus here on acoustic wave propagation, but the principle is similar for other wave propagation problems. So we'll consider linear acoustics, where we have our balance of mass on the left-hand side and our balance of momentum here on the right-hand side. The unknowns are the acoustic pressure and the acoustic particle velocity. And we have material parameters, the density rho I and the speed of sound Ci. The index I denotes that this might be different in different media. And we know we can combine this into the linear wave equation, where we have a speed of sound as the material parameter. Here an index I is missing. Also, this can, of course, change for different media. If we now want to simplify this a little bit, for one-dimensional problems, we have the 1D wave equation, where we simply have a spatial coordinate xi. So the Laplace operator just gets the second spatial derivative. Okay, so what happens when wave propagates in 1D. So we consider essentially a plane wave propagating from one domain omega 1 here on the left to another domain omega 2 on the right. If the material parameters are inhomogeneous, the incident wave will be partially reflected and partially transmitted. And we can define the reflection coefficient from the wave impedance Z by this given formula. So the difference in impedance over the sum of the impedances. So how is this reflection coefficient actually defined? It's defined as the amplitude ratio between the reflected and the incident wave amplitude. And then we have the acoustic impedance. We know this from acoustics. It's simply given by the density times the speed of sound. And we can clearly see from this relation already, if we have impedance matching, Z1 is equal Z2, we have a zero reflection coefficient. So that's what we want to obtain. So that's the basic idea of the perfectly matched layer already, impedance matching. And in fact, we are free to choose the material parameters C tilde and rho tilde in the perfectly matched layer region. Since this is an artificial region, we can do whatever we want that has numerically appropriate properties. And here is a choice that is suitable. We make them complex valued. We say the speed of sound in the PML layer is the speed of sound over 1 over J. Sigma, where J is the imaginary unit, and sigma is a damping function. And if we set the rho to this expression, we can clearly see we have impedance matching, since rho tilde times C tilde is rho times C, the original impedance of the domain 1. So we have introduced the damping function sigma. Sigma is real valued, J is our complex quantity, and we set, if we set the damping function to 0, we can also see that we recover the original expressions. Okay, so let's look a little bit what this means, having a wave equation with complex valued wave numbers. So we have we had the wave equation already in time domain given. We can transform them into frequency domain by doing a Fourier transform or simply using the harmonic ansatz. And what we get here is then the square of omega instead of the time derivative, and also the sign has changed. So this is essentially the frequency domain formulation in 1D. And here we can clearly see that we have a general solution of this equation, which can be given here by this standard wave solution. However, our wave number here is now complex valued, since C tilde squared is complex valued. And if we do the math, we find out we have the original non-damped wave with a real valued wave number times a decaying exponential. So it decays with increasing spatial coordinates. So what we have here is we see that the wave number k in the propagation domain and the wave number in the damping domain, they are actually related by this 1 minus j sigma term. And again, we see if we have sigma equals 0, we recover the original formulation. And we also see that the sigma determines the amount of damping we get in our wave propagation problem in the perfectly matched layer. So we have seen this works perfectly in 1D. However, in 2D and 3D, we have an issue because oblique incident waves are not that easy to treat. So here we can't use the simple reflection coefficient. Actually, we have to change the impedance formulation. We have to take the angle of incidence into account. However, since every wave can be decomposed as a sum of plane waves in the principal coordinate directions, we can choose a Cartesian perfectly matched layer. Here around our domain of interest, we always cut parallel to the coordinate directions, and we decompose the waves into the respective coordinate directions. We can do this with any wave, and in these areas here we decide, okay, we do our damping in y direction. We have no damping here, but in x direction we have to set our damping function greater than 0. In the corner regions we have damping in both directions, and here again we only damp in y direction. So this is already the general idea. It turns out this idea can also be interpreted as a complex coordinate stretching. And this is actually a very elegant way to derive this perfectly matched layer formulation for the general case. In the 1D case, we've seen more physics-based interpretation with the damping factor in the exponent. And now we look at this complex coordinate stretching. So we define our perfectly matched layer coordinates, always denoted by the tilde. So the x tilde can be mapped to the original x by this expression. And the choice of this expression is actually suitable. With this, we can also obtain the derivatives, just derive with respect to x, then we get 1 plus sigma x over j omega. Since this integral drops here, and this we decide to call eta x. And then we can use this definition to actually write down how the differential operators transform. So a partial derivative with respect to x tilde is equal to 1 over eta x of the partial derivative with respect to x. And also here we see, in case of a 0 damping factor, the etas are equal to 1. The mapping is trivial, the identity map, and the etas are 1, so also no mapping is done for the differential operators. So if we use this mapping now and regard it as a coordinate transformation, we can modify the original Helmholtz equation in the mapped coordinates, so to say, and obtain this mapped formulation here written in the scalar notation. We can also write it in vector notation. And here we have to introduce these scaled nabla operators, where you have seen the expression of the transformed derivatives. And from this, you can also straightforwardly obtain the weak form by multiplying with the test function, integrating over the domain, and applying the divergence theorem. This was done here with homogeneous Neumann boundary conditions, and you see that also the area element is transformed, or the volume element, so to say, is transformed by the product of the mapping functions. And again, for the 0 damping function, the stretched or mapped formulation and the original formulation are strictly equivalent. So in a sense, you could say you apply this stretched formulation in the complete domain, but in some cases, in some places of the domain, you want to make it the original formulation by simply setting this damping function to 0 there. It does not have to be spatially constant, of course. Okay, so that also brings me to the damping functions. What is a suitable choice for the damping function? It turns out it's actually important to choose a good damping functions, and a few useful choices are given here. The first choice is using constant damping. This is useful because it's extremely simple. A bit better maybe is a quadratically increasing damping. So it increases from 0 because the mapped coordinate is defined as 0 at the start of the layer until the value sigma 0 at the end of the layer, because L here is the thickness of the layer. And in fact, a very good choice is for the wave equation is the inverse distance damping function, which will create an unbounded PML. You can imagine if x equals the length here, the denominator gets 0, and we have an infinite damping at the end of the layer. And it can be proved that this inverse distance damping is optimal for the Helmholtz equation. All the above damping functions are implemented in OpenCFS, so you can try out the performance of the different functions there. If we now go to the time domain, we want to switch from the modified Helmholtz equation, which is frequency domain equation, to a time domain formulation. And this we can do by doing an inverse Fourier transform of the formulation seen before. However, there we have convolution integrals arising. And in there are formulations that actually solve these convolution integrals, but they can actually be avoided by introducing additional auxiliary variables. In particular, you need one scalar variable and one additional vector valued variable. So in 3D, the PML node will have 5 degrees of freedom. One, the original pressure, another one, the scalar valued auxiliary variable, and 3 for the vector in 3D. So perfectly matched layers in time domain will increase the system matrices size drastically. What is also an important issue in time domain is the stability of the perfectly matched layer, since it might become unstable and introduce waves instead of damping them out, especially in longer simulation times. Okay, just a few practical guidelines for setting up a perfectly matched layer. What do you have to consider? First off, use the same spatial discretization in the perfectly matched layer region as in the propagation region. It turns out about 2 finite elements along the thickness of the perfectly matched layer are quite sufficient. In the frequency domain, I should say. In the time domain, you usually need a little bit more. Inverse distance mapping, the damping works best. We've seen there's a proof for optimality there, and a layer thickness in impinging direction of just 1/8 of the wavelengths is often sufficient. Here there was a study done with the error, and of course you can see the larger you make the layer thickness, the smaller the errors get, and the better you resolve the mesh size here. So H is the mesh size in the layer. The finer you resolve, the better the error gets. Okay, so now we want to switch over to infinite mapping and to elliptic partial differential equation. So we can also imagine that open domain problems are common in elliptic partial differential equation. Just consider electrostatics, where the electric field is usually not just bounded at the end of the domain, but decays until infinity. However, as with wave propagation, you can't model an infinite domain. The same holds for magnetostatics or magnetodynamics in this case. You have waves again. And also solid mechanics problems. Just imagine a hole in an infinite, a pressure-loaded hole in an infinite domain is maybe a useful model for tunnel construction. You don't want to model the whole extent of the mountain around the tunnel, but want to efficiently truncate your domain. So what if you don't do any special boundary treatment here with the truncation, this truncation must be sufficiently far from the domain of interest, from the region of interest. And the modeling errors are introduced by the truncation. And in fact, one option to remove these modeling errors are infinite mapping layers, which are very similar in the idea of the perfectly matched layer. That's why the similarity in name. In fact, we've done a paper on the infinite mapping layer more or less recently. And the basic idea here is we map the infinite physical domain xi to a finite computational domain xi tilde by using a so-called mapping function. So the mapping gives us the model coordinates as a function of the real coordinates. And this is equivalent to the PML. We simply introduce now called xi relation for the derivative. And then we simply do a coordinate transformation similar to the perfectly matched layer. And just to show you how this transformation works here, we have done it as at the example of the Poisson equation. Here for simplicity, we insert the coordinate mapping, and what always comes in when you do coordinate transformations is a Jacobian matrix here. This is the J, and of course you also have to take account for the volume element here, dx tilde, where you need the inverse of the determinant of the Jacobian. So here are the relations for the differential operators. As you can see, they're equivalent to the perfectly matched layer and the relation for the volume element. Okay, so when can you use this infinite mapping layer? Typically you define a mapping layer around the domain of interest. You can use similar discretizations as with the perfectly matched layer. Then you use your mapping functions. We've investigated exponential mapping, tangent mapping, and rational mapping. You have to, in fact, pick a suitable mapping function for different physical problems. For example, when you consider deep water waves, the exponential function is the wave amplitudes decay exponentially. So here the exponential function is the ideal map. Similarly, in electrostatics, you have rational decay. So this is a suitable mapping function in this case. As I said already, we've tested this formulation for electrostatics, solid mechanics, and water waves, and also these formulations is available in OpenCFS. Yeah, this already brings me to the references here. I've put them here so you can look up the details of the things I presented. And we have a few questions for learning reinforcements. You can prepare your answers to the